Okay, so I'm going to look at a second example of calculating the pH of a weak base titrated with a strong acid. Let's bring one of these up. So in the previous example, the strong acid was the excess reactant. Let's take a look at this one. An analytical chemist is titrating 133.1 milliliters of a 0.4400 molar solution of propylamine, C3H7NH2. The propyl is the C3H7. It means the NH2. With a 0.8400 molar solution of HNO3, nitric acid, strong nitric acid. The pKb of the propylamine is 3.46. And we want to calculate the pH of the base solution after the chemist has added 43.2 milliliters of the HNO3 solution to it. Note for advanced students, you may assume the final volume equals the initial volume of the solution plus the volume of the HNO3 solution added. Round your answer to 2 decimal places, okay? Cool. So let's take a look at this one. So we have those numbers written down there. What's the first step in doing calculations of acids and bases, titration calculations? I hope you remember it's to write the chemical equation, right? So what we do is we write the chemical equation. So nitric acid, I'm going to put the acid first. We're going to react it with the propylamine, C3H7NH2. And then those are going to form. So, this is not really a double replacement reaction. We don't have like sodium hydroxide, HNO3. We have a nitrogenous base. So typically you treat it as a Bronsted-Lowry. You donate the H+, transfer the H+ from the acid to the base. So that'll leave us with NO3-, right? And then this, you're going to put the hydrogen on the nitrogen, so make it NH3+. It's the nitrogen that's acting as a base, not the carbon, okay? So now, what we can do is we can write down our numbers. So let's do our initial moles. And we're going to do millimoles here. So let's do the HNO3 first. So the HNO3 is 43.2 milliliters times the molarity, which is 0.8400. Okay, so 43.2 times 0.8400 should get 36.288. Okay, that's our HNO3. Remember, the liters cancel and you're left with millimoles. So now let's do the propylamine. The propylamine it's a larger volume, 133.1, but a lower concentration, 0.44. Okay, so look what happens when we do this calculation. 133.1 times 0.44. See how we get a larger number? So that means this is the excess reactant. And this is the limiting reactant. Okay, the previous example was the opposite. The acid, the strong acid was the excess reactant. So I'm going to write our initial moles here. So for the HNO3, 36.288. And then for the propylamine, 58.564. These are 0 to begin with, right? Then they react. The acid reacts with the base. Boom, boom. Subtract the smaller from each one, the limiting reactant. The maximum amount of anything that can react is given by the limiting reactant. These are going to go up, right? These are going to go up by 36.288, 36.288. And so then once the reaction is done, at the ending, this is 0. It's all gone. So the HNO3 has been used up completely. It no longer affects the acidity. The difference here, I think, is 22.276 millimoles. Let's check that just to make sure. 58.564 minus 36.288, 22.276. And then these are going to be 36.288, 36.288. And there you go. Now, here's what we have. We have a weak base. In fact, that weak base has a pKa, I'm sorry, pKb, right? Bases have pKbs, not pKas, of 3.46. That's a measure of how strong the base is, how basic it will make the solution, okay? Now, what about over here? What do we have? We have a conjugate base. So that's also a base, but it's of a strong acid. Remember what we said about that? The conjugates of strong are negligible. So if you have a strong base, its conjugate acid doesn't affect the pH. If you have a strong acid, its conjugate base doesn't affect, okay? So no effect on pH. Very little anyways. This one, on the other hand, is a different ballgame. This one is a conjugate acid of a weak base. And remember from chapter 16, the weaker a base is, the stronger its conjugate acid is. So since this propylamine is a weak base, its conjugate acid is also a weak acid. So it's going to act like a weak acid. So what do we have? We have a conjugate base, I'm sorry, we have a weak base with its conjugate acid. That is what we call a buffer. So this titration has actually created a buffer. It's made a buffer solution that will resist the changes in pH. Okay, that was our previous section, right? So now, how do we deal with that? The Henderson Hasselbach, right? pH equals pKa plus the log of the concentration of the conjugate base over the conjugate acid, the concentrations of them, right? But we don't have a pKa. We have a pKb. What do we do? Well, if you have a weak acid and you have its conjugate base, this one has a pKb, this one has a pKa. And you might be able to think a little bit about what they would be equal to. I'm going to, just to remind you, from chapter 16, we had this, Ka times Kb equals Kw. I don't know if you remember that. So just like with pH and pOH, remember pH plus pOH equals 14? We have the same thing here. pKa plus pKb equals 14. I could prove that to you more, methodically, but it turns out to be the case. So that's pretty cool. So now what we can do is we can use that pKb to find pKa. The pKa of the conjugate acid is just 14 minus the pKb. Cool, right? So that's 14 minus 3.46, I think is what I wrote down, which is 10.54. And that sounds about right. So what that means is this guy right here has a pKa of 10.54, the conjugate acid. So that allows us to directly use the Henderson-Hasselbach equation. There is another equation that people derive where it's the pOH equals the pKb plus the log of the concentration of the conjugate acid over the weak base. And then that gives you the pOH, and you find the pH from that. But this one works, this is a fine way to do it as well. You just take 14 minus the pKb, and that will give you the pKa. And then you can use the Henderson-Hasselbach equation. So for this one, that would be 10.54 plus, just make sure it's the base over the acid. So the base, this is the base over here, right? So the base, the amount we have left over is 22.276 millimoles. And then the amount of acid that we have is 36.288 millimoles. Now, again, you might say, well, wait a minute, this has to be concentrations, not millimoles. You could divide the millimoles of the conjugate base, of the weak base, divided by the total volume, perfectly fine. And then divide that by the number of millimoles of the weak acid divided by the total volume. But in both cases, you'd be dividing by total volume, so they're going to divide out anyways. So again, this is nice. You can just put the millimoles in instead of actually figuring out what the volumes are. So I know that this is a little bit messy, but I'm going to bring it down here. So there's going to be 10.54 plus, and then I'm just going to go ahead and take the log, and I'll put this in parentheses, of 22.276 over 36.288. And that's a minus 0.2119. So that's the same as just subtracting it. And it looks like you get 10.33. Okay. So all I did was I took the 10.54, the pKa, and then added this negative 2.119. Why was it negative? I know it's negative because this number in the numerator is smaller than this number in the denominator. So that means the ratio is less than 1. The log of a number that's less than 1, like 0.9 or 0.8 or 0.7, is going to be negative. So we're going to get a negative 0.2119, not a positive 0.2119. Okay. So one way you can make a mistake is you get those two numbers mixed up. So I just want to check, make sure we want to have the acid in the denominator, right? It's the conjugate acid in the denominator, and then the base in the numerator. That's what we have there, because the base is this one over here. Okay, so those are your two types for that particular problem. So just like the strong base with a weak acid, when we do a strong acid with a weak base, there's two possible outcomes. One, there's actually three possible outcomes, but we're looking at two of them. One is where the acid is in excess. The other one is where the base is in excess. And our calculation of the pH depends on which of those two outcomes we have. If it's a strong acid excess, then we just figure out how much strong acid we have left over after the reaction, calculate the pH from that. If, on the other hand, the base is the excess reactant, then we're going to have this mixture of the weak base with its conjugate acid, which means that we're going to use the Henderson-Hasselbach equation to figure out what the pH is. There's actually a third possibility, which is that they're equal, that you have equal amounts, which would be the equivalence point of the reaction. In that case, what would happen is you would just end up with no acid, no base, but you'd have conjugate acid on the product side, and the conjugate acid would determine what the pH is. Okay. Take care.